Hi, this is Alex from devstories.eu. Mastering DeepChem, episode 6 of 15. You build a model on a new chemical dataset, run your validation, and get 99% accuracy. You deploy it, and it immediately fails in the real world. Your validation metrics confidently lied to you because of how you divided your data. Today, we are looking at scientifically aware splitting, specifically comparing the default random splitter with the random stratified splitter. You might assume splitting data in DeepChem is exactly the same as using a basic train-test-split function from a general machine learning library like scikit-learn. That is a common misconception. General-purpose splitters work well for simple single-label arrays. DeepChem splitters are engineered to natively handle complex multitask environments, sparse Boolean labels, and the specific data structures DeepChem uses to store molecules. Let us start with the default approach, the random splitter. This tool behaves exactly as the name implies. It takes your loaded dataset and assigns the chemical compounds into training, validation, and testing sets uniformly at random. If you are working with a perfectly balanced dataset where your active and inactive compounds occur in equal measure, this random shuffling works fine. But scientific data is practically never balanced. Consider a toxicity dataset like Tox21. In the real world, the vast majority of chemical compounds you test are safe, and toxic compounds are relatively rare. Suppose only 1% of the compounds in your dataset are flagged as toxic. This is a severe class imbalance. If you pass this dataset through a standard random splitter, pure statistical chance dictates that your validation or test set might end up with 0 toxic examples. If your test set consists entirely of safe compounds, a model that simply guesses safe for every single input will score 100%. You end up with a mathematically perfect score for a completely useless model. This is where the random stratified splitter becomes mandatory. Instead of blindly throwing compounds into buckets, stratification forces the split to respect the actual distribution of your labels. The random stratified splitter scans the properties of your dataset before dividing anything. If your overall data contains exactly 1% toxic compounds and 99% safe compounds, the splitter guarantees that your training set has a 1:99 ratio, your validation set has a 1:99 ratio, and your test set maintains exactly that same proportion. Here's the key insight. DeepChem datasets usually involve multitask learning. This means a single chemical compound is not just evaluated for one property, but often for dozens of different biological assays simultaneously. The labels across these tasks are highly sparse. You might only have a handful of positive hits for one specific toxicity assay across 10,000 rows of data. The random stratified splitter navigates this multidimensional matrix. It ensures that those extremely rare positive hits are distributed fairly across your splits. Every subset of your data receives a representative slice of the active compounds, preventing any single task from losing its minority class during the split. Without this mechanism, your model evaluation relies completely on luck. For highly imbalanced, multitask scientific datasets, stratification is not an optional optimization. It is a fundamental requirement to prove your model actually learned the underlying chemistry instead of just exploiting a statistical blind spot. Thanks for spending a few minutes with me. Until next time, take it easy.